everyone, in this section, we will study the quotient set. As always, let us first take a look at its definition. Let A be a non-empty set equipped with an equivalence relation. The quotient set of A modulo this relation is the set consisting of all equivalence classes of A under this relation. Each element of the quotient set is an equivalence class of A, that is, a subset of A. In other words, the quotient set is a subset of the power set of A. To illustrate this idea, let us look at a very simple example where A is taken to be the set of integers. We will define the following binary relation on the set of integers, where an integer x is related to an integer y if and only if 2 divides their difference. In other words, x is related to y if and only if it has the same parity as that of y. It is straightforward to show that this relation is indeed an equivalence relation. Moreover, under this equivalence relation, we have two equivalence classes. The first one is the equivalence class represented by 0, that is, the set of even numbers. And the other one is the equivalence class represented by 1, that is, the set of odd numbers. As a result, Z modulo this relation is our quotient set, which consists of two elements, namely the equivalence class represented by 0 and the equivalence class represented by 1. Now if we take a closer look at these two equivalence classes, we notice that they have some nice properties. First, both of them are non-empty sets. Second, these two classes are mutually disjoint. That is, there is no integer that is both even and odd. Third, their union is the whole set of integers, meaning that given whatever an integer, it must be either even or odd. In other words, we have now partitioned the set of integer into two parts, the set of even numbers and the set of odd numbers. Given an arbitrary integer, it must belong to one and only one part. This observation motivates the general definition of a partition, which we introduce right now. Let A be a non-empty set. A partition of A is a collection of subsets of A indexed by a set I, satisfying the following three conditions at the same time. Number one, any subset in this collection is non-empty. Number two, any two distinct subsets in this collection are mutually disjoint. Number three, the union of all subsets in this collection is the set A itself. Essentially, this definition simply means how we cut the set A into different components, and each component Ui in this partition is called a cell of the partition. Now, using this new terminology, what we have concluded in the previous example can simply be restated as the quotient set of Z modulo that equivalence relation forms a partition of Z. Actually, the aforementioned result can be easily generalized into the following theorem, which is the central result of this section and reveals an intimate connection between the quotient set of equivalence relation and a partition. So here it is. Let A be a non-empty set equipped with an equivalence relation. Then the corresponding quotient set forms a partition of A. To prove this, we only need to verify that the quotient set satisfies all the three conditions characterizing a partition. To begin with, pick an arbitrary equivalence class represented by X. Then, this equivalence class is non-empty as it contains at least X, as requested by the reflexivity. Second, consider two equivalence relations represented by X and Y respectively, such that they are not identical. Then, according to the proposition we proved in the previous section, if two equivalence classes are not identical, then their intersection is empty. This proves the pairwise disjointness. Last but not least, let us prove that the union of all equivalence classes is the set A itself. On the one hand, take an arbitrary element X from A. Then, by reflexivity, X belongs to the equivalence class represented by itself. Since it belongs to one equivalence class, it belongs to the union of all equivalence classes. This proves one inclusion. On the other hand, since each equivalence class by definition is a subset of A, so will be the total union of all such classes. This proves the inclusion in the other direction, and in turn implies the desired set equality. The intuition behind this theorem is actually quite simple. It basically states that if the set A has an equivalence relation imposed on it, then each element of A belongs to one and only one equivalence class. In other words, we can classify elements of A into these distinct equivalence classes. That's it. To illustrate this idea, let us again consider several different equivalence relations imposed on the set of real numbers, and try to figure out in each of these cases how the set of real numbers is partitioned into corresponding equivalence classes. First, let x be related to y if and only if x and y are equal to each other. In this case, each equivalence class represented by x is a singleton set containing x itself. In other words, if we consider each real number as a point on the real axis, then this whole axis is just the union of all these individual points. Next, let x be related to y if and only if the absolute value of x is equal to the absolute value of y. Under this equivalence relation, each equivalence class is either the singleton set 0 or a pair of real numbers which are negations to each other. Visually speaking, in this case, you can imagine the real line as a union of the origin as well as infinitely many symmetric pairs. Keep going, let x be related to y if and only if either the product of xy is positive or x and y are both 0. Under this equivalence relation, there are three equivalence classes: the set of positive numbers, the set of negative numbers, as well as the singleton set 0. Now, visually speaking, it suggests that we regard the real line as three parts: the origin and two rays towards different directions. Last but not least, the universal relation, where each x is related to each y. Under this equivalence relation, there is only one equivalence class, that is, the set of real numbers itself. Thus, under this equivalence relation, we don't cut R into any small pieces. Rather, we keep it intact. Alright, hopefully this gives you a general idea how the quotient set modulo and equivalence relation can be used as a partition of the original set. As the last remark of this section, we briefly mentioned that the other direction works as well. Indeed, if we are given a partition on the set A in the first place, we can then construct an equivalence relation based on this partition. More precisely speaking, let P be a partition on A. Given arbitrary elements x and y in A, let x be related to y if x and y are in the same cell of the partition. One can easily verify that the binary relation defined in this way is indeed an equivalence relation. Moreover, the equivalence classes are precisely the cells in this partition. So now we have the complete picture between the quotient set and the partition.